Okay, we can start. Uh, what I was going to tell you about today is how would you solve this optimization problem in the non-negative factorization matrix case? Um, Last time we had a non-negative matrix. And the goal was to write it as a product. As a factorization of two non-negative matrices. That's how I wrote the matrix. Here, W and H are non-negative. So again, I want to like explain more the point of view of like the least squares approach of the do here. Like same as what we're doing in the matrix, in the ordinary matrix case, where in the ordinary matrix case, like even if you have even if you know the rank of the matrix, you may want to try to find a matrix of lower rank or a factorization of lower rank that close enough to the matrix A. So here, the idea is that I want to find a low rank approximation, low non-negative rank approximation. Okay. So you're trying to find the minimum of these functions, right? But the difference with the regular case is that you're trying to minimize this function subject to constraints, right? Because it's subject to the fact that both of the entries of both W and H should be negative. So these are great excuses to talk about optimization with constraints. How it the force of like right multiply. Is the correct way that you can that you have seen partially before, but not in to the full extent. By these inequalities, I just mean that each entry is not negative, right? So it is an optimization problem with constraints, but again, it's not an optimization with constraints before from how three the constraints for inequalities, this is a little bit different with the very inequalities, right? So I'll tell you about how that works. So I'll explain the case first. Again, saying that you have a function of the matrices is the same as saying that you have a function of the entries of the matrices. So really, you only have to understand the case of a multivariate function. And this is at the end of the day, like a multivariate function. So I'll explain like if you had a function of n variables subject to constraints, how would you find the mean of that or what must it satisfy? Um,
So so you're trying to find the mean.
so you're trying to find out the mean of a function of n variables where the x well let's say that you have a vector x of variables. So basically, the mean is not being taken over like any arbitrary point in Rn, but rather the vector x has to be belong to a set, which will be a complex set. So I'll start kind of like more general, then kind of like narrow it down to what you care about, but it's kind of like useful because I was thinking, like I look at all the computer science, I look at the courses in computer science and engineering, and I couldn't, and even math, couldn't find any course that kind of goes over convex optimization, like that I can like obviously in an obvious way. But I do want to kind of like say how do you deal with these like because convex optimization is one of the most important things, like you know oh okay. And graduate exactly of course it's not. Why isn't there no one goes to the very like that makes no sense to me. Like so you can at least give like a a sneak red drops like what is the main idea like just to have like something in the back of your head like um
Oh, so I'll be a bit German from today, where K represents like the convex set. I think like in German, like is with the K. So here K subset of Rn.
again what do you need to be a convex set? It means that if you take two random points on the set, the disegment between those two points is entirely contained within the set. So
I'll do just a picture. Well, let me call them x1 and x2. So if x1, x2 belong to the set, then for any t between 0 and 1, t x1
plus one minus px2 is in the set. Okay. And if you kind of like go through the formula that corresponds to a point the line segment x1. So convex sets someone tons of useful properties, otherwise like a very important case. In fact, I will specialize in a couple of minutes to convex sets which come from matrix inequalities. So that will be where I'll analyze this more carefully.
So the main example for today, those are the types of sets that you deal with linear optimization. So if you ever took linear optimization, that's basically what you study all the time there. So you have a matrix A and K consists of the vectors in Rn.
have to battery check, then you figure out that stuff that is convex.
Just to maybe, just to do a quick example, these are like the ones that you'll see in linear optimization.
So this triangle is a convex set of R2 and is defined by three inequalities. If you think of, let's say that
This is a triangle. The vertices are 0, 0, 1, 0, 0, 1. So one of the edges is x plus y equals 1. And so the inequalities
right, x plus y needs to be not be bounded by red line, and x and y have to be positive or non-negative, right? Like into the convex set. Did you want to rewrite it in this notation, right? Because in this notation, all the variables are on the left side.
So you just have to play a little bit with the formula. So
like, saying that x is positive is the same thing that minus x is negative. So now it does look like,
and then you can read off these like as a matrix, because this would be 1, 1, negative 1, 0, 1 times x, y. That's equal to 1, 0, 0. So in this case, this would be the A. And this would be the B.
so you can always, and again, you can always rewrite all these here, like, this these are like these convex sets that come from linear matrix inequalities, like, you can always, you may need to play around with that for a little bit, but you can always rewrite them in this format. AX, whatever. So the main part, like the first question is, right? I'm more, first I need to more in positions like where comes to the. So one exercise that is like you have to get lines to your line and the lines to the side. The second, right? Right. Like the second is still within that. Yes. Yeah. So in this triangle, if you choose to put the triangle, the line segment. So that's our triangle. Of course, there are convex sets to for nonlinear inequalities. For example, the inside of a disk, you take the unit disk that is convex, but that is not like given by linear inequality, but it's x squared plus y squared that are equal to 1, right? So and then there are more interesting cases, but already like the matrix inequality case is important enough to understand. Okay. Okay, so first let's just talk about what was a regular main in the unconstrained case where there are no restrictions on x, right? If there are no restrictions on x, right?
If x mean is a local mean for the function,
Then we know that if you're a local mean, in particular, you have to be a critical point, right? And if you are a critical point, then its gradient should be 0 at the local mean, right? That's the same for like a local max, there's not specific local mean, but that's like what you would call like a necessary condition, right? It has to happen for sure.
sorry, the gradient, right? The gradient at the mean would be zero. I think that might be. Now, in the constraint case, it's a little bit not quite the same. So in the constraint case, it, um, on the convex set, you have an inequality. It's not an equality, so I'll explain why. For any for any x in k, sorry. At least sufficiently close to the, let's say close enough. Yeah, to x. Because it's a local mean, not a local. So let me explain what the main difficulty could be in this case. So the idea is that if you have a convex set, right? I'll try more kind of like an addition so that you don't think it's necessary. I just do for an equation. If I would indicate is true of any convex set. The thing is like now the mean can occur kind of like in the boundary of the convex set, right? Like so, if you have a convex a mean in the interior, when you call it the interior, then it's totally fine. What I was, the condition of continuity applies, so the gradient has to vanish if the local mean happens to be on the inside of the convex set. But there's a possibility that the local mean, you know, there's a possibility that the local mean happens at the edge of the convex set at the boundary. Let me color it. And what does it mean to be a local mean? It means that you're a mean relative to nearby points, right? Like points are close enough to you. But if you are a local mean, you don't, if you're inside the convex set, you don't care about what's happening outside the convex set, right? Because like that's why it means to be a local mean relative on the convex set. So you only care about the points on inside the convex set. You're saying that for any of those points on this convex set, close enough, then the value of the function here is less than the value of the function at other. So not all directions are available at that mean, right? Because for example, you cannot move in this direction because that's outside the convex set, right? So that is the main difference. So the idea is that if you take a point inside the convex set, which is close enough, because it's convex, you can connect them, right? You can connect them with the line segment. Like you can connect them with the line segment, which is entirely contained in the set, right? And that line segment has a direction vector, right? There's a direction vector. It's kind of like the relative vector, like x minus x mean. So let's think about what the direction of derivative in that direction. So the direction of derivative in the direction of that vector. Well, there are two ways to think about it. First is the dot product of the gradient, like at that point, sorry, at the point x mean. First, it is the dot product of the gradient with the direction vector. Okay, so. And B was just x minus x mean. So that's one way to think about what the number should be. Oh, that I thought I was thinking about actually say that. I mean, honestly, if you look at it, like you don't need it to have like unit length. This formula is still like fine, like even when it does have like unit length. If you use like the formula in terms of the limit of the which is the number I'm going to write down, like actually it doesn't require like the vector coming in and it's like this is like a convention that's used in how to create. But if you use the limit definition for the directional derivative, which is the limit as t equals to 0 of f of x mean plus tv minus f of x mean divided by t, right? Which is that's actually when we talked about gradient before, like I mentioned this formula. Okay. What happens here? This is a limit as t equals to 0. So if this is a local mean, right? If this is a local mean, this is going to be a bit less. It's not going to be larger than this other bound, right? Because this other point, where is this other point located? This is, it's somewhere along this segment. So if you think of t going between 0 and 1, at time 0, you're at x mean, at time 1, you are at x. So between 0 and 1, the x mean plus tv is somewhere in between. So because this is a local mean, the value of the function here should be less than the value of the function at this other point. So this difference is always non-negative. And that's always great. And that automatically tells the limit of non-negative things is non-negative, like with inequality. Okay. So then that is like enough because like that just means that this dot product has to be greater or equal. Is that okay? Some cases. Right, because it could be like, it doesn't have to be like, like the, right, because if you get up far away from, if you like, say, for example, like just to say a silly case, like if the point were here, maybe there, that does allow another local mean, so you cannot guarantee that this difference, like, right, because it is a limit, so you're being taken closer and closer to, well, I guess, yeah, like, in the end, right, it's just, let's see, in fact, right, I guess we don't really need the point to be close enough because no matter how far away you start with the limit, you always go, so eventually, yeah, like, we can even count the condition of like, there's being like, you being like, So like close enough, because like if the directional derivative, only requires, eventually you get close enough, but because in virtue of the limit, not how far away you started, what? Yeah, I think that would be fine. Yeah. For any x and k. I mean, it will be close enough once you take the limit, but like that's fine. Like the limit kind of like takes care of it actually.
Okay, and then the other, the reason why convex sets are useful is because there's a separation lemma for convex sets, which is related to something called Farkas lemma.
If you have linear optimization, so I'll tell you about that now.
The picture will make it possible for people to prove. But the idea is that if you have a convex set,
And you have a point which is not on the convex set.
then the point can be separated by a hyperplane. By or in this case, it would look more like a line. So
So you can separate from K using a hyperplane or like a line.
by separating, I just need that the point would be on one side, but that's why it has to be a hyperplane because only a hyperplane is not like a generalization of a plane, right? So no one divides the space into halves. So if the point is on one half of the line or the hyperplane, and the convex set lies on the other half of the hyperplane.
On the hyperplane.
Kind of looks silly maybe in this picture, like obvious, but like the convex sets doesn't even have to be finite in size, right? Like it could even be instance trivial, but there is something that needs to be true there, like it is because again, like a convex set, like like a convex set, like for example, could be like the first quadrant, but like can be intermediate extent and so uh again, like in certain cases, it's kind of obvious from the picture, but again, like this is supposed to work in any dimensions and bunch of other things, so I think it's not, but like the picture kind of like hides the fact that he's an important, no. Uh, if I, so now how do I want to use this? So. So there is a version of this tag that I want to use for the case of the airplane, but this is from forecast lab. Okay, which I'll tell you about now. The forecast lab is a very useful result in linear algebra. Okay. So let me see, how should I explain it? That for discussing a forecast lab is we have to talk about what the tone of vector, what is the code generated by from vectors in in the in on our end. Okay, so let me talk about that first. Well, let's say they do not n vectors, they have n vectors. Okay. So here you have n vectors in our n. So the cone generated by those vectors generate a what's called a cone, and that consists generated by A1, A2, up to AM. Consists of the vectors B that can be expressed as a following linear combination. And then, so the are the vectors that can be written as a linear combination of these vectors. Uh, with the condition that each of these positions that you express as a linear combination of literally are non-negative. So each of these positions has to be non-negative. I'm just gonna like show you a picture of what this looks like.
So here's an example. Let's say that the vectors, just to do something in R2 where I can draw it. Let's say one of the vectors is one. And the other vector is let's see. Well, let's see. Let's say 2, 1, and the other vector is 1, 3. Yep. So the 2, 1 is somewhere in here, maybe. And 1, 3 is maybe somewhere in here.
So if a vector is in the cone,
Right? If the vector B is in the cone of these two vectors, if B belongs, let's call it the cone of A1 and A2.
again, that means that you can express P as a linear combination of A1 and A2, but with the extra condition that the coefficients are not negative, right? So P is a linear combination
Of C1, A1 plus C2, A2. So if you call just B, B1, B2, right, you know that it would be C1 and 2, 1 plus C2, 1, 3. Okay.
everybody is like equations, you know.
Or 2C1 plus C2 equals B1. And C1 plus 3C2 equals B2.
But okay, so you have to solve. So what you're trying to solve here is a system of equations subject to the extra constraint that the variables are not negative, right? So it's not just solving linear algebra, it's not like just like the linear algebra problem, right? Because linear algebra, we don't care what the variables are, right? Like whether they're positive or negative, right?
You want to, you have this extra constraint.
And if you were, like, you know, you can go to algebra, and you just drop on the science, like it's not to um, but to like it literally looks like a curve. It's like oh, like a curve. So like
The what, this can be solved. This can be solved provided B is in here. So I'll show you where it's supposed to lie. So again, like imagine like there's kind of like two lines here. There are two lines here determined by the vector, right? And there's a cone in between those two lines, which is just like color the region in between the vectors. Let me see if I can draw it out. That extends forever, right?
so the idea is that if the vector B happens to be inside the region in the matrix, that is when this system of inequalities can be solved. I mean, inequalities together with inequalities, right? It's kind of a mix.
So if the vector B happens to be in here, anywhere in here, that's when you can solve the system of that.
Oh, that's like even like for example here, like if I had like a third vector A3, like like you like in this case it's kind of like it's fine, it's just like it's a bit redundant because like having like
For example, if my third vector A3 had been in here, right? That doesn't really add anything to the cone because the cone is kind of like, in this case, would have been determined by the extreme rays.
what if A3 is like in yeah, but that's like well in that case the you know it is fine like like it would be kind of like an extreme case, but okay, it's like a degenerate cone. You know what I mean? Like like it's better just to keep calling that a cone, even though it wouldn't look like like I guess what you're saying, Brett, is if you slowly start rotating A2, so that well, you have to be careful, right? Like it depends on how you do it, like because that's still too complex. Right. Oh, yeah, definitely will always be a convex set, which is the only thing that I care about. Right, but if you start to like rotating A2 into facing towards A1, it kind of like makes more of like almost like half the plane, then maybe different. Well, I guess if A2 becomes minus A1, yeah, we would have to. Right, like you just get the line, exactly, you collapse it with the line. Yeah, but that's still convex, Yeah, it just has no insight, we kind of like care more about the ones that have insight. But what I thought that this, what you were asking, like, if you had like four more vectors, the idea, if you have four more, like two more vectors, right? They're still kind of like a cone, but it's not. Like some of them are superfluous, like they don't really add anything to the cone, right? Because kind of like the cone is in a sense determined by the furthest yeah. That's kind of so how it looks like what I wanted to say is as we're getting like hopefully it's plausible.
And if you had like in 3D, like in 3D, yeah, like the cone kind of like, if you have, it really always does look like a cone. Like, let's say if you had like just four vectors to kind of like show what I mean, then the cone is kind of like determined by the extreme ones, like in a sense, right? And then the there you see like the cone. So it's not that you need there's no restriction in the number of vectors.
Is that some of them may not add anything. Uh,
No, what I was going to say is that just to kind of continue with this example.
As always, if you want to write this in the notation, you would write it as 2,
2, 1, 1, 3 times C1, C2 equals B1, B2. So what is 2, 1, 1, 3? That would be oh, that's just A1, A2, so
So one way to characterize the cone is that a vector is in the cone, right? If you make a matrix with columns are the A1s up to AM, right?
I think I have here like I'm messing up, like the notation, like Okay, it's fine. Like it's just not the usual, if A is a matrix whose columns are A1, A2 up to AN. Okay, so like that's like it's annoying because the matrix is size n by n. It's like the size like like I should have like done it the other way, but like A is size. You have m column vectors, right? It's like my mistake, but you kind of like know what I mean. It's just like important to understand what happened here, right? You have n column vectors, each of size n because you already know n. So kind of like interesting. Then B is in the cone of A1 up to AN, provided that ACB can be solved. If you can solve this equation, together with the constraint that together with the constraint that the coefficients are not negative. Is that okay? That makes sense. And right, as we were discussing, it happens to be the case that this is set, right? So the cones are convex, like so a cone of A1, A2 up to AN is convex. Okay, and then Parkin's lemma. Okay, it is way more interesting than it sounds like. But it's kind of like nice to understand geometrically what's happening. So again, this is a condition. This defines a condition for the vector B to belong to the cone. Right. So this is what defines B belonging to the cone of the matrix. Like the cone of the matrix is just the cone of the columns of A, right? So this is what it means to say that B belongs to the cone. Okay. So what Parker's lemma says is either B belongs to the cone or something else happens. Okay. So Farkas says that there are two things. So Farkas. So only two things can happen. Has anyone taken linear optimization or? So you talk about that when you talk about the duality theorems and all this stuff, if it rings a bell. So one of two things happens. Okay. One option is that B belongs to the cone of the matrix, right? So B belongs to cone of A1 up to AN. In which case, it either looks like the picture I had before, the draw cone and the B somewhere in there. Like this is like the possibility. Or what is the alternative? The alternative, I mean, if either you belong to the cone or you don't, right? Actually, if you don't belong to the cone, that's the other possibility, right? But what does it mean to not belong to the cone? It means you don't belong to the convex set. And because of the separation lemma, you can separate it by a line. So the other option, right? Like this is option one, or B does not belong to the cone, right? Okay, like either you're in or you're out, right? But if you're out, that means that B maybe looks like this. Like, I don't know. Let me just draw the picture so that it looks easy for me. So maybe the vector B somewhere there is a funding cone
But because the cone is a convex set, the separation lemma, what it says is that you can separate the cone from the vector D to a hyperplane or a line.
Okay, so you because of the separation lemma for convex sets, you can separate the two. Okay,
But what does it mean to separate it? It means that you are on one side of the plane and on the other side of the plane. But what does that mean? Remember, a hyperplane where a plane has a normal vector, right? Like that. That's actually the generalization. I mean, maybe I should have said that at the beginning of the class, right? But what is the general equation of a what is the general equation of a plane? Like, like from top three, ax plus by plus bt equals b, right? Which you could, if you think of the normal vector as being abc, right? Plus n dot x, y, z equals b. The important thing is that the normal vector, sorry, the plane had a normal vector, right? A hyperplane in one dimension is the same idea. You just call it, I don't know, like a1, x1 plus a2, x2, blah, 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 an, xn, right? Maybe I should call these n1 and like mix them up. Well, then n1 and 2. This is not, no, this is not the equal circle. Yes, take it back. The letter n is in some spots in the sometimes. And then there's a hypervector. I mean, there's a vector, right, that is like the normal vector to the hyperplane vector. And so the equation of a hyperplane, you can still write it as n dot x equals b. Right? Like, so like a hyperplane still has a equation.
so all that I'm saying is that because it's a hyperplane, it has a normal vector.
Of course, the normal vector was not uniquely determined, right? But like in safety, like you can kind of like choose it. I'll choose it so that kind of pick one thing the same. It makes an acute angle with the vector b. So uh, so the idea is that the angle between n and b is at 90, but because the convex x is on the other side, the angle between n and any of the vectors that are in a convex set, the cone, would be obtuse, would be more than 90. So the dot product would be negative, right? Because remember, if the dot product is positive, it's acute angle. If the dot product is negative, it's obtuse. So the separation lemma is that
Says that you can find a vector n, which will be the Lagrange multipliers, by the way, very soon. These are going to be the lambdas.
well, I mean, it's basically yes, almost like the lambda set.
Well, the lambdas will appear in at some spot in this moment, like So the Lagrange multipliers will show up soon, but you can find that the Lagrange multipliers actually were,
I mean, are these ones, not the s. Like this would be the lambda, but
I'll tell you more about that in a moment. Such that n dot b is positive, and n dot ai is negative for every I.
no, that is. It's kind of like useful to write it down algebraically what Parkas lemma says, because if you write it down algebraically, it's definitely not obvious at all. Like the geometric interpretation makes it kind of like plausible, but if you write it down algebraically,
What this is saying is that there are two possibilities. So what Farkas says is that either this system can be solved or um, or you can find a vector n that satisfies and these can be written also uh, these can also be written as um you know in matrix notation because the transpose of the matrix, you know. Let's see, and that should be fine, I think. Oh, and this should be less, I guess, this should be less or equal to. Oh, do I have it? Shit, I wrote it down. I mean, one has to be very opinion. Yeah, this is fine. Right, if you transpose like the matrix, right, like the rows, you know, of this matrix, would be the vectors A1 into AM. And so this would be the dot product between the rows and the vector n, so that has the correct size, right? Because what, okay, how many, let's see, and no, where is B? Where did B live? Um, right, like so A was like again, like terrible notation, but A was n by m, right, which is a usual opposite size convention. So right, A transpose would be m by n. A transpose would be n by n, and the vector n was supposed to have n entries because we're all like all the vectors are n. That's fine. Oh, right. Oh my God, good catch. Right, like which means that every entry, yeah, like it's less. But if you think about it, like, I mean, if you just give this system of inequalities for someone and tell them, oh, one of these could have to be true, then you stare at it and you're like, okay, what's going on here? It's not like obvious at all, you know, like it is like algebraically, it is saying something really useful, like and you'll see how that's supposed to work. Okay, at least I'll write down the statement today. Like the proof is super short, but like it may be easier, it may be better to do it next Tuesday. But at least I'll show you what the main idea is because the proof is not too bad. But okay, so the idea is that let me write it down. So these are called the KKT conditions. Like after the three people who can describe them. So you if you open any book convex optimization it looks like okay, maybe KKT conditions like place correlation. So what it's saying is that let's say you're trying to okay, let's say you're trying to solve this optimization problem. So you're trying to solve you're trying to find the mean of a function where x belongs to a convex set. And the convex set is going to be given by matrix inequalities. Okay, so usually you would just write A X, that's where you can see I messed up the sizes like before, like it really leave with the transpose, right? Because the transpose, I mean, I'm going to use Marcasema eventually, but to compare it to the, like, the transpose is the one that was like N by 10, right? So like, this is like the one that you need for you to make sense. But if like typically, like it doesn't really matter which is called A and which one is called A transpose. But you can always think about the sizes so that it matches, to figure out which one should be which. But like just the way I'm thinking about it, I'm thinking of the matrix A as being, like the one whose columns generate the cone when I use Markov lemma, so that's why I have to write it this way. So what the KKT conditions do is characterize a local mean. So what it says is that if you have a local mean, if X yields a local mean for the function, then you can find lambda 1, lambda 2, up to lambda n, and you can find numbers so these are going to be like Lagrange multipliers. That's why I'm calling them lambda, which are all non-negative. So if you remember, when you do the Lagrange multiplier case, like in part 3, like there's no condition of the lambda whether it's positive or negative. That's a little bit different because they're working with the equality, right? But here they're going to be equality, right? That's why it changes a little bit. But we're going to be able to find lambda numbers, lambda 1, lambda 2, up to lambda n, which are all non-negative. So all of them are non-negative. By the way, I should have said this before I started, but go back to before I finish for today. And Lagrange multiplier, right? The usual way in which we solve the Lagrange multipliers without 3 is like gradient of f equals gradient like lambda times the gradient of g, which is a more elegant way of writing this is that gradient of f minus lambda g is 0 vector. That's like a more nice way to write it. And if you have multiple constraints, right? If you have, this is always when there's not a single constraint. If you can have like multiple constraints, like equalities, what you have to solve would have been something like. So like if they're all constraint equations, if G1 is set to constant, if G2 is set to constant, etc. Okay, so that's kind of like how you set up the Lagrange problem. And if you absorb, you can always obviously absorb the minus of the lambda, so you can just write it as you just redefine the lambda. What I'm saying is that in the equality case, there a priori you cannot say whether lambda should be positive or negative, but it could be anything. In the local mean case, when it's like these inequality constraints, a lot that have to be non-negative. That's not like what happens. So satisfying that. So here, this is AI. And the thing here is that because they're linear inequalities, the gradients are super easy. They're just like the vectors, right? The linear inequalities. Like you only see, you don't have to write the gradient of the constraint. It's like it's just take the vector and stuff and determine the inequalities. So you get that, and
the lambdas satisfy what's called like a complementary slackness condition.
And moreover, yeah, I'm almost done. You have the, which again, if you take linear optimization, you'll see that a lot, like slack variables, like and all that stuff. Complementary slackness condition, which is that lambda for each, for I equals 1 to up to m, lambda I times a dot x minus b has to be 0. So, I'll be I, sorry. Oops. So what this is saying is that either lambda I 0 or this combination a dot x minus b on the. Again, that's what happens, just to compare to in linear optimization, what you have that optimization problem, you can find the dual, and then the dual are going to branch multiplier, that's the original problem. So this is not something that you see also when you use the dual optimization of the optimization. So it's either this scalar is 0 or this other scalar is 0. That's what's one. But again, like, the proof is not too long because it's just now because we have the Forta 7. The Forta 7 is kind of like the machine that you throw at it, and it's really fun. But yeah, I'll explain you how the proof works like on Tuesday if that sounds good. And then I'll tell you how to apply it to the non-negative matrix factorization case. So like you kind of using how it starts wrapping around very fast. It looks like I'm here. Yeah, I think that's gonna get 2 6.